Good evening. I really feel that I should begin with an apology. We'd hoped that by now Austin's comet would be a conspicuous object in the morning sky with a bright head and a long gleaming tail. And sadly, it isn't. This photograph, taken some time ago in Japan, makes the comet look quite impressive, but it's not really at all conspicuous. This drawing by Paul Doherty does show a bit of a tail, but when I looked at it the morning before last, I couldn't even see it with the naked eye. I could, of course, with binoculars, but it's not bright, and I'm afraid it's not going to be, which is very sad indeed, although it should remain on view for some time yet. On the credit side, you remember the Giotto probe that went through Halley's Comet in 1986? Well, it survived the encounter. It is still under control, and in the next few days, attempts are going to be made to turn on the camera and see whether it still works, and it may do. And, of course, we'll bring you news of that as soon as we can. And then the Hubble Space Telescope has at last been launched. It was sent up safely from Cape Canaveral, and after a few hitches, the solar panels which power the telescope were successfully unfurled. And so all seems now to be set fair. And I think the Hubble telescope is going to tell us a great deal. Don't expect any really spectacular pictures and results yet a while. It's going to take some time. There's a lot of calibration and checking to be done, but as I say, it does look now as though the Hubble Space Telescope is at last safely in orbit. And now, on to our main theme for this evening. When is a star not a star? The answer may be when it's a brown dwarf. And that seems rather puzzling, but it may not be. And we may now have identified the first authentic brown dwarf. And here it is. You can see it there on the end of the arrow. And this, of course, is a negative picture, so the stars appear as black against a white background. Now, an ordinary star, like the Sun, begins its career inside a mass of dust and gas known as a nebula. As it contracts by gravitational force, it heats up inside, rather in the same way that the air inside a pump will become heated when you pump up a cycle tower. And when the temperature reaches a certain critical value, nuclear reactions begin, and the star begins to shine. Basically, what happens is that hydrogen is changed into helium with release of energy and loss of mass. And our Sun is, in fact, losing mass at the rate of 4 million tons every second, though I hasten to add that there's plenty left. But if the mass of the forming star is not great enough, it will never be able to start nuclear reactions in that way, and it'll never really quite get going. And that may be what we call a brown dwarf. Now, in our solar system, the most massive planet is Jupiter. And Jupiter is far more massive than the Earth. But Jupiter is not nearly so massive as an ordinary brown dwarf. And I've got a demonstration here to show what I mean. Now, this globe represents Jupiter. In this glass, I have 318 dried peas, and they represent Earths. And if you don't believe there are 318 there, count them as I pour them down. Now, Jupiter is 318 times as massive as the Earth, and so our 318 dried peas will just balance Jupiter. Now, consider Jupiter itself. This time, in this pan, I have 10 Jupiters, bearing in mind that each one of those is 318 Earth masses. And here we have our brown dwarf, only about the same size as Jupiter, but very much more massive. So you can see 318 Earths equal 1 Jupiter, 10 Jupiters equal 1 brown dwarf. So a brown dwarf is very much more massive than the Earth. But stars do differ very much, both in size and in mass. Consider, for example, the brightest star in the sky, Sirius, the dog star. And that's a hot white star, and it's very much larger than our yellow sun. But the Sun itself is larger than a red dwarf, such as Barnard's star, which is only 6 light years away, very much less powerful than our Sun. And then consider a white dwarf, such as the companion of Sirius, Sirius B. Now, this is quite different. This was once a large star that has collapsed on itself. It's used up all its nuclear energy and is now shining very feebly. Very small, very hot, and very dense. In fact, if I could fill a glass with white dwarf material, it would weigh a great many tons. And now, what about our brown dwarfs? Brown dwarf being a missing link. That's nothing like so massive as a white dwarf. It's just kind of missing link between the star and the planet. And obviously, we've got to see them when they are comparatively close to us on the cosmic scale. And that involves measuring star distances. And this is done by the method of parallax. Now, the Earth goes around the Sun at a distance of 93 million miles. Let's observe a star at one end of the Earth's orbit. We see it at position A, so it's somewhere along that line in direction A. 6 months later, we've moved round to the other side of our orbit, and we are now seeing the star in position B. Now, that doesn't mean the star has actually moved from A to B. It merely means that it's a comparatively close star, and we are seeing it from a different kind of direction. And the star, our brown dwarf candidate in this case, is actually there, and seen in changing position by parallax against the background of more distant stars. And that's how we can tell that a star is decidedly close to us. But because brown dwarfs are so dim, they're difficult to see. And they look faint because they really are faint. As we've said, our new candidate has only 1/20,000th the luminosity of the sun. And this means they are very difficult to find. One astronomer who's been looking for brown dwarfs is Dr Mike Hawkins of the Royal Observatory, Edinburgh. Mike, welcome to the Sky at Night.
Thank you.
Why were you searching for brown dwarfs?
Well, I was actually searching for another class of star, cool white dwarfs. These are also high-proper motion stars. And among the sample of stars I picked up were some very red stars, which looked interesting, and I thought at the time might be brown dwarf candidates. I certainly wasn't expecting to see such stars there.
But of course, there have been previous searches for brown dwarfs.
Yes, indeed. Over the last several years, there's been intensive searches for brown dwarfs, and they've mainly concentrated on looking for companions to brighter, more massive stars, to narrow down the search area. When a massive star has a less massive star orbiting around it, the effect of the
orbiting companion.
The orbiting companion is to move the more massive star slightly. Basically, both stars are orbiting around a common centre of gravity, which lies slightly to one side of the more massive star and has the effect of causing it to move slightly relative to the background of stars. Of course, the less massive star is moving a lot, but it won't be detectable against the brightness of the larger star. But that movement would be a signature for the presence of a companion. Now, in practice, for a brown dwarf companion to a more massive star, the movement will be so slight at the distances we'd expect to see the system that it's not really a very feasible way of doing it. It's actually more relevant to look for planetary searches. But this orbit does have an additional characteristic in that it's not just the physical movement, but the velocity which changes as well. And there will be a systematic, periodic change in the velocity as the stars orbit around each other. This is a typical diagram showing the change of velocity as a function of position in the orbit, and then one can see quite clearly that there is a systematic motion there which would indicate the presence of a companion. A more direct approach to the to searches involve looking at the spectrum of a star. And here we see some observations with white error bars. Superimposed on that, a typical white dwarf spectrum. And the observations fit quite well in the right-hand, the blue part of the diagram. Going towards the left, where at the redder wavelengths, there's clearly an excess of flux. And this could be attributed to the presence of a very red companion with a spectrum like the red line. And one would basically be looking at a superposition of the two spectra, and one could deduce that from that there might well be a red companion. Unfortunately, the situation is not completely unambiguous, and there are other possible interpretations of that situation. Perhaps a more convincing example can be obtained from a very modern instrument become available to astronomers, an infrared camera. Here we see some frames from the camera. The squares are individual pixel detectors, and what one can see in the left-hand frame, in a relatively near infrared band, an image of a white dwarf star with really nothing else in the frame. Moving to the central picture, which is further to the red, one can see new objects that appeared in the bottom part of the picture, and going further to the right in the reddest of the bands, that object is now brighter than the original white dwarf image. The interpretation of this is that we're seeing a very red object which is putting out most of its energy in the very red bands, and is presumably a companion, and probably a brown dwarf type companion to the star. Unfortunately, these searches near bright stars don't help us to answer the most important questions about brown dwarfs. The first one is exactly what is the nature of such stars, and when they're so close to a very bright star like that, it's very difficult to make really detailed subsequent observations because of the contamination from the primary. And the second question concerns the statistics, and that's an even more important question. And again, when a star is a companion, the one's really getting statistics of stars which are companions and not the population as a whole, which would include free-floating stars, so to speak.
Well, we have one very promising candidate now. How did you discover it?
Well, by searching from photographs, large photographs taken with the UK Schmidt telescope in Australia. This is the largest photographic camera in the world, and it takes plates, 35 centimetre square plates, covering some 6.5 degrees by 6.5 degrees on the sky. Here's one, and you can see there's a bright galaxy there, a cluster of stars there, some bright stars. There are some 200,000 star and galaxy images on the plate. To give you some idea of what a large field we're talking about, the full moon, if it were to appear in the field, would be something like the size of that tenpenny piece. So we're talking about a very large area of sky indeed. Now these plates, in order to be of use to scientists, have to be quantitatively measured. And for this purpose we have, in Britain, developed some high-speed measuring machines. And the one I was using was the Cosmos measuring machine in Edinburgh, which is one of perhaps the most powerful machine in the world of this type, and it's an area of technology which Britain really doesn't have any rivals in. The way it was used to measure the photographic plates was that it scans the plates in each plate in about 3 hours or so, and detects every single image on that plate and measures a number of parameters describing the image, such as the position, the size of the image, its orientation and shape and so on. And these are stored on mag tape and can then be used by astronomers for more quantitative or statistical work.
What's the next step when you search the plates with the Cosmos?
Well, we are looking for stars with large proper motions, and this is done by measuring a plate taken in, say, 1980, which this plate is, and the candidate star is marked with an arrow. A plate taken in 1989 of the same field shows the star to have moved to the bottom left, and this indicates a large proper motion, some 7 arcseconds in 9 years, easily detectable by the machine. The other parameter which we're interested in is the colour, and this can also be obtained from the photographic plates. This is a red passband plate, and we see the image is quite faint compared with the star just to the right of it. If we look at the field in the infrared band, we see that our candidate stars is now actually appears to be brighter than the star to its right, indicating a very red colour relative to that nearby star. This colour difference can be understood more easily if one looks at the spectrum of the star. And here we see the spectrum with the red band on the left and the infrared bands on the right. And the two pass bands of the photographs are shown, the R band, which is a red band, and the I band, which is shown in purple. And you can see that there's very little flux indeed in the R band pass, whereas the I band has a significant amount of flux in it, and that accounts for the relative appearance of the images on the photographic plate. There's more we can learn from the spectrum. If we look at the spectrum of a previous, one of the previous coolest stars known, LHS 2397A, we see the vanadium oxide band marked as VO. This is a band due to absorption by a molecule, and it's a good indication of temperature. Flicking back to our Brown Dwarf candidate spectrum, we see that that band is significantly deeper, indicating a cooler object. There's more we can learn from the spectrum too. If we look at the top right, we see a sharp line marked FEH, an iron hydride line, which is only associated with dwarf stars and is not seen in giant stars. Going back to our new spectrum, that line is again present, indicating we definitely do have a dwarf star there.
How confident are you that MH18 really is a brown dwarf?
The thing which brought the star to prominence was the measurement of its parallax. Having seen it as a good candidate, we did need to know its distance, and this took 2 years to measure. But just recently, the measurements which were done in the States were finished, and from this it appears that the star's much nearer than we originally thought, and making it much less luminous, and indeed making it the least luminous star known in the sky. And to be sure that it's a brown dwarf, one unfortunately needs a little bit more than that. We need to know its mass. Now, mass is very difficult to measure for isolated stars. The best way of measuring stellar masses is from a binary system, but unfortunately this star isn't a binary. So the only other way is to use a theoretical relationship between luminosity and mass. And this shows that the star may be have a mass as small as 5/100ths of a solar mass, and is almost certainly less than 8/100ths of a solar mass, which would mean that it is a brown dwarf. The critical mass for a brown dwarf, in other words, for a star which can't burn hydrogen, is 8/100ths of a solar mass. And so it does look like a very strong candidate for such a star.
Because brown dwarfs are so dim, there may be plenty of them around that we can't see. And as we know, there's plenty of material in the universe that we haven't tracked down yet, the famous missing mass. Could that missing mass, do you think, be due to swarms and swarms of brown dwarfs?
There are two ways of measuring mass for any particular system. One is to simply look what one can see, assign a mass to it, and add it all up. The other method is to deduce the mass from the motions of the stars. These will be moving under their mutual gravitational field, and by making measurements of their motions, one can work out how much mass is involved in their motions. Now, whenever this has been done on whatever scale, one always finds more mass deduced from the motions than we actually see, and this is basically the missing mass problem. Another aspect of it is that the problem seems to get worse on larger scales. We're talking about perhaps a factor of 2 near the Sun, maybe up to a factor of 10 for the galaxy as a whole, and 100 or 1,000 on the scale of clusters of galaxies or the universe.
Well, certainly brown dwarfs are fascinating things, and I just wonder, what would a brown dwarf look like if we could see it from close range? Here's an impression by Paul Doherty, an ordinary star in the background, and there, in fact, is the brown dwarf itself, and I wonder, would it really be like that? Of course, you certainly couldn't walk about on the surface of a brown dwarf, the temperature about 2,000 degrees, and yet you can't regard it as a normal star. And how would you compare the mass of our hypothetical brown dwarf with, shall we say, that of Jupiter, which we normally regard as a planet? What's the limiting?
Well, there's no lower limit been defined for a brown dwarf. What makes Jupiter a planet is that it's in orbit around the Sun in a planetary system, and that's why it's not considered to be it's considered to be a planet. But in terms of mass, nobody's really put any particular limit on a lower mass for a brown dwarf.
Well, I'm quite sure that the searches are going to go on. What about the Hubble Space Telescope? Is that going to be of any help to you here in your searches for new brown dwarfs?
Unfortunately not. The Hubble Space Telescope has a very narrow field of view, and so it would look straight through the galaxy, and would be very unlikely to intercept a brown dwarf in our galaxy. One needs to look at very large areas of sky to have any hope of finding these stars.
So we're back again to observation carried out from the surface of the Earth, and I imagine that you're going to go on hunting in the near future.
Oh, indeed, yes.
Well, let's hope you succeed, because these brown dwarfs, they almost certainly exist. We have now a really good, new, promising candidate, and I think they're going to be of immense importance in astronomy. So for the moment, from Mike and myself, good night.